Mhm. Mhm. Yeah. There we go. Yeah. It's like, oh, you're so close. It's like it's Friday morning, right? Your presentations are like Monday. You got so much time. Yeah. How's the game coming along? Well, I'll take a look at it after. Oh, that looks awesome. Yo, they're right there. It's fine. Whatever. Yeah. Yeah. I don't know, man. That seems cool to me. Um, today, today we're talking about. Okay, so I'll be upfront about this. Today's lecture not particularly connected to the curriculum, right? We completely understand that you're in the middle of midterms right now, right? You're totally in the middle of midterms, right? So I'm not gonna throw like a whole new set of things that you have to do, um, for your midterm project or even just as activities, because today is week 4, day 5, and what's the title of today's lecture? Yeah, I like how you say that with a question mark at the end. Yeah, user authentication. And why is that question mark there? Why are those question marks? Yeah, we've we've done it already, right? And you're absolutely right. You have done this already. So we'll do just like a little bit of verbal review. I'm not gonna be writing really any code today. I might show you some code, but today's really gonna be more of like an exploration of sorts. We're gonna dive a little bit into some computer science, and see what that is. Um, but but I want to stress that today's lecture is more in the vein of like an advanced lecture. These like advanced topics. They're just kind of fun to talk about. I don't at all expect you to take the things that I talk about today and bring those into your projects, especially since you shouldn't have user authentication in your project, right? You shouldn't be checking for passwords or all that stuff, right? I know some of you have probably started doing that, right? Have you? No? Okay, good. Have you? No? What about over there? No user auth? Good. Good, good. Um, that's fine. This here is just gonna be we're taking a little bit of time to just hop into something that's sort of interesting. Um, or it's sort of interesting to me. Now, when I say user authentication, that's just the title of the lecture, but I'm going to be diving a little bit more instead in cryptography. Whoa, make some crypto, bro. Yeah, we're gonna, so so we're hopping into some cryptography, and we'll take a look at what that means. Now, to start off this lecture with a little bit of pizzazz here, I'm gonna write a secret message. Oh, right. All right, one sec, one sec. I'm baking up the secret message. All right. Does anybody here want to be a confidant? Is that the word for it? Yeah. Yeah. Anybody want the secret? I got my digits on here, like my bank digits. Yeah. Yeah. No, no. This whole what is this like? Boot camp is just an extended episode of The Bachelor. No, here we go. Uh, yeah. One lucky boot camp student. No. So there's a secret message on there. I'd like you to take a look at it. But keep it secret, keep it safe. All right, is that pretty clear? Yes. Okay. I will be asking you a series of math questions. What, Kelly, were you impressed by my accent there? Yeah, yeah. It was my pompous, like, like orator voice. So I will be, asking you a series of math questions. Yeah, it's my thespian voice. And I'll have you kind of like answer those questions. And we'll take it in turns where everybody but Sebastian will answer the questions and then you will, right? We'll see just how smart y'all are. What is 2 plus 3? All right, good try. What's 2 plus 3? It's 7. Aw, boo-hoo. Boo-hoo. All right, what is 4 plus 2? All right, 9. What's the answer? It's 6. Yo, get with the system, y'all. What is... Here's a tough one. What is 12 minus 1? Yeah, what's 12 minus 1? 21. That came out of nowhere. Any intelligent? No, I'm kidding. Any 121. Sure. What's the answer? It'd be 13, right? Obviously, it would be 13. I don't know, but like, who do we even let into this boot camp, Archie? What's the admissions process like here? Yeah. So we got some numbers here, and I'm very disappointed in your basic math. So there's something interesting going on, right? I'm communicating. I'm saying something. The rest of y'all trying to decipher what I'm saying, having like a miserable failure of a time figuring out what my secret messages are. You and I, we got this line of communication, even though it's going through public channels, right? Even though I'm yelling this out loud, we've got this stuff figured out. And, maybe over time, y'all would be able to figure out what's going on, right? And be able to come up with a pattern, which I know you sneakily tried to do. Right? Maybe given enough time. But off the bat, at least we can have a bit of communication. We've set up is essentially like a protocol that has a key, right? Some way to decipher what the communication is. And we're going to spend a good chunk of this lecture really just analyzing that one interaction that we've had. So, we exchange something physically, right? So we've met up and exchanged what I'll call a key, right? And then every bit of communication, can be understood only by the person with the key. Okay, what is the key? There you go. Wham. Add 2 to every odd number, evens stay the same. So add 2 to every odd, evens stay the same. Now, this here, what we essentially have is an algorithm, right? We've come up with an algorithm for making some like communication where the fact that the algorithm is a secret makes it tough for whoever is listening to understand what's going on, right? It's not a very complicated algorithm, right? Add 2 to every odd, even stay the same. It's an algorithm that really only works with numbers at the moment, right? But, maybe we can imagine that this kind of algorithm could be used on words or on images or really any kind of data, right? In fact, when we send words back and forth, like through a network anyways, it's all as zeros and ones, which are numbers, so maybe we'd be able to do something similar with this stuff. Now, this whole thing kind of relied on the fact, and this is something we'll really dive into, that we needed to meet up and exchange messages physically. Okay. So, what we have, this kind of like algorithm is something that I'm going to call something like a cipher. And cipher is going to be like a really simple kind of change to some input that can then be reversed. So this whole add 2 to every odd, evens stay the same. I mean, I could even write it this way. Or I might say add 2 to every odd, add 0 to every even. And then what I'm noticing here is that I've essentially got some parameters, right? This could be add x to every odd, add y to every even. And now, like, this algorithm here could be boiled down to essentially an x-y pair, right? I could make it public, like publicly known, that every odd number is going to have some value added to it, and every even number is going to have some value added to it. Right? Everybody could know this. And as long as I secretly exchange the x and the y, right, these secret keys, right, even though the algorithm itself is public knowledge, right, people intercepting the messages won't be able to figure out what's going on immediately, right? They won't know because they won't have the key to unlock it and be able to draw that correlation, right? So in our example here, what we did was, like, I physically had you shout out the answer, right? But if we're talking about computers, right, and that's what we're kind of making our way towards, is if I have to communicate securely between multiple computers in a network, right, the computer at the end, when it receives a message, is not going to broadcast out to everyone, like, hey, this was the answer, y'all. Like, it's very much a secret, right? But it's possible, it's 100% possible for agents along the line, like agents along the network, to sniff and listen to packets of data that are being passed through, right? So that's gonna be a big thing for us, as we're gonna look at a couple different examples, is that people in between, you know, A and B can still grab information as it passes through the physical wire, right, or as it passes through the air. You can still grab information and try to read it, right? But if the information has been encrypted and they don't have the key, they can't read it, right? So often it's totally possible, right? If I'm sending a message from here to, like, somebody in Iran or whatever, right? Like, my message is going to have to pass through many points in the network. I don't have a direct line. So I can't trust that there isn't going to be somebody halfway through that opens up the message, reads it, and then sends it off, right? Secretly. I just can't trust that that won't happen. Okay, so this whole thing here, I'll say that XY, like, we'll say this is like the key, right? This is the key, and this thing here, that's maybe like the algorithm. And this particular algorithm is of a class called ciphers. An example of a cipher would be a thing called rote 13. And this is something everybody's really played with in one way or another as a kid. If I take GHIJKLMNOPQRSTUVWXYZ, if I take, I got it right on the first try. Whoa. Can everybody just whoop? I mean, that's cool. If I take all of the letters in the English alphabet, right, and I rotate each one by a certain number, such as 13, meaning A turns into N, you know, S turns into F. What I've got all of a sudden is a way to write messages that seem like gibberish until somebody knows what the algorithm is. So here I might write, you know, it's ya boy, and this here would be using this cipher. This would be turned into let's see, V, G, and then F, and then L, N, and then O, B, I. Vigflun oib, O-B. Right? Nobody knows what this means. Did I get that right? Oh, whoops. V. Yes. Vigflun ob. Right. Now, the first time somebody sees this, if they don't know that rote 13 is happening, they're going to be confused. Right? She's like, I don't know what's going on. Right? I don't understand. If somebody finds out that it's rote 13, easy. Super easy to turn it back. But we could turn this from rote 13 to something like rote x, right? And again, as long as me and the person that I want to talk to meet up at some point and have that conversation, right? And say, hey, look, this is the number that you're going to be rotating by. Then anybody who intercepts vg ulnobv, right, they're going to be at a loss. Right. Now, for the upcoming kind of things that we're going to look at, there's three names that are going to tend to pop up. There's Alice and Bob. Oops. Alice wants to talk to Bob. Bob wants to talk to Alice. And Eve is sneaky. Sneaky, sneaky Eve. Right? So, at some point, like, I'll bring the whiteboard up. But there will be Alice trying to send a message to Bob, or vice versa. And Eve is somewhere in the middle, just kind of snipping out little messages, right? Trying to read them. Trying to get access to their secret interactions. And really, our whole thing is that over the course of the lecture, we're going to look at how can Alice send secret messages to Bob? Hey. Vice versa as well. How can Bob send secret messages to Alice? Because that's a different question, right? How can Alice or Bob ensure that the messages they receive are actually from, Bob, Alice? Right? How can we ensure that and, not something that Eve put together? Right? And these are things that are, are going to have kind of analogies or applications in web development, right? Again, I want to stress that the stuff that we're learning about today, this is not stuff that you're actually going to apply as a web developer. It's just cool to know what's going on underneath. You might find it interesting, and in that case, like, come do computer science. It's a good waste of 6 years. So, so these are the things that we're going to try and, our goals. Plus, I'm going to put one more goal down is, how can Alice and Bob exchange the keys, right? Exchange the keys that they're going to need for communication in a non-dumb way, right? Because if I need to set up secret lines of communication between me and another place, such as Nima and Facebook, right? Right, or Nima and WhatsApp or whatever, right? Communication or Nima and TD Bank, right? Stuff that shouldn't be able to be sniffed, right? Stuff where like somebody's not able to take a magnet and hold it over the wires, right, next to my house and be able to like read my bank account info. We need some way of encrypting that information. So there needs to be an agreement between me and TD or me and Facebook, right? And you've done this, you just maybe don't know. Now, when you sign up for Facebook, let me take you through the process. We go to facebook.com. Facebook.com, and we go to, oh, okay, I would like to sign up for one book, please. Nima, Lighthouse, mobile or email, email at email.com, email at email.com, password, email, birthday, March 29th, 1994. Oh, wow, I totally would have assumed that Facebook would have had an other option. That's really surprising. Well, and then sign up. Is it my birthday? Yeah. And then in a couple minutes, Mark Zuckerberg leaves. Oh, there's already somebody with an email at email.com. All right. Mark Zuckerberg, he gets a little notification. He's like at his office just coding or whatever he's doing. And he's like, ah, god damn it. Another person in Vancouver just made an account. And he gets, he leans over to the big fishbowl that he keeps on his desk. That's just lots of little loose scraps of paper. He picks another one up, and it's just an assortment of letters and numbers and symbols. Puts it in his pocket, gets on the train, right? Takes the train all the way up to, Seattle maybe. Maybe it doesn't come all the way up here. He just doesn't want to spend money to take it all the way to Vancouver. And then he hitchhikes up. And then the doorbell rings here at Lighthouse. And he's like, hi, I'm here for Nima, special delivery. Shows up. Well, here's your secret code. Anytime you want to send a message to Facebook, just make sure that it's encrypted with this key so people in between can't read it. All right, I've got another one. I gotta go. See ya. Somebody in Pakistan just made an account. I gotta hop on a flight. Like, it's not feasible. It doesn't work. So we gotta figure out some technological or mathematical way of exchanging these keys. If only there was some key exchange. If only there was some Diffie-Hellman key exchange, right? The whole point of our algorithm kind of focuses on the fact that we need to establish some algorithm that can happen, right, for encrypting and decrypting messages, right? And the algorithm needs to be able to encrypt and also decrypt, right? Like, I need to be able to not just jumble up letters, but also dejumble them. So that rote 13 is pretty easy. You rotate 13 once, then you rotate 13 twice. If it was wrote by whatever number, you could wrote and then unwrote. So the algorithm needs to exist and be public, at least, or agreed upon. But the keys, they need to be exchanged in a smart way. So enter the Diffie-Hellman key exchange. Diffie-Hellman key exchange. Does anybody know why it might be called the Diffie-Hellman key exchange? Anybody want to throw out some random obvious guesses? I don't know. Why would it be called the Diffie-Hellman key exchange? Yes, the two famous goldfish named Diffie and Hellman. All right, so conceivably there might be two famous, proper nouns. Two famous people that invented this key exchange. Okay. It's a good guess. The two goldfish. Two famous goldfish. We're going to find that the answer to this, like, seemingly silly question is actually a little bit more complicated. I hope you know at this point that, like, part of why I ask questions in lecture isn't just is not the Dora the Explorer kind of. I mean, I kind of do go by the Dora the Explorer school of pedagogy. Does anybody see the lake? Where is the lake? Actually, speaking of which, has anybody seen the trailer for the live-action Dora movie? Okay, genuinely, Dora live action. I'm going to put this in the notes. And this thing is actually really cool. If anybody wants to go watch live-action Dora with me in this year, hit me up. So, the Diffie-Hellman key exchange is a really interesting picture here that'll help us kind of understand what's going on. Can I open this image in a new tab? Is it visible? Oh my god, that's not legible at all. Okay, so here are some names, as I'll call them, actors in our scene. There's Alice and there's Bob. Now, the keys that I'd shown before, or the keys were like numbers, right? They were numbers. In this analogy here for this picture, they're going to be paint, right, or like paint colors. But then we'll talk about how that stuff translates over into numbers soon. Okay, so Alice and Bob want to establish some kind of line of secret communication, right? So maybe they've decided on an algorithm that would be used, like rote 13 or something. But they need that secret key to be established. So Alice and Bob can both publicly agree on a common paint color, right? Because our keys are going to be paint colors here. They could agree on a common paint color. They can agree on this in public. Alice might say, hey, how do you like the color yellow? Oh, I love the color yellow. Awesome. Our color is yellow. Right? Easy. Whatever. Anybody can know that. And then Alice and Bob both come up with their own secret colors that they don't tell each other. Right? Secret colors that they don't tell each other and that they don't broadcast. So Alice might have come up with this, orange-red situation. And Bob might have come up with this turquoisey situation here. Right? That stuff has not been told to each other. But since they both are aware of the common paint color, they can do a fairly simple operation, which is merge the two colors together to come up with two colors like this. Now, in this example here, right, in this hypothetical situation, the idea is that you can have colors be merged together quite easily, but separating the colors is virtually impossible, right? Or it might take a lot of time, right? I don't know if you've ever tried to unstir paint before. It's a good task to put your like baby cousin on or something. Or I don't know if you have like a particularly annoying kid. Unstirring colors is virtually impossible. So these stirred combinations, right, they can be transported in public because anybody who intercepts this stuff is going to be unable to split the stuff apart and find out what the secrets were. Now, at this point here, Bob and Alice have exchanged their combination colors, right? So Alice now has the blue and Bob now has that orange. And the thing is, Alice still has their secret color that they'd never shown anybody. Same with Bob. Bob still has their secret color. So what they're able to do is now merge together the color that they'd received, that merged color, with their secret. Both of them are able to do that. So if we were to like kind of write this out, like Bob might have gone, so common might be blue. Bob might have picked red, and Alice might have picked yellow. And the reason I'm writing this out is because what I want us to see here is that Alice can make yellow plus blue, right? Bob makes red plus blue. Then when they exchange, Alice gets red plus blue and adds yellow for a total of red plus blue plus yellow, right? Bob gets essentially the same thing. Bob gets yellow plus blue and adds red. Did I get that right? Yeah. So Bob ends up with yellow plus blue plus red. Whoops. And the interesting thing about this operation is that this way, both of them end up getting the same combination of colors that involve those two secret colors plus the common, right? And merging colors together, that's an operation that doesn't need to have its operands in order. I can do red plus blue plus yellow or yellow plus blue plus red, and I end up with the same color, right? That's the interesting thing here, is this stuff can be done out of order. And now what we've ended up with is Alice and Bob both end up with a common secret color, right? A common secret color that nobody else is able to know because Alice was never in possession of Bob's secret. And Bob was never in possession of Alice's secret. They only ever actually dealt with their own secrets or weird combinations of the two. This way, nobody else has that common secret, and it's only exchanged between these two people, right? So ideally, like the two of us would have been able to do that from far away, right? So this here, like the analogy here is done with colors. Right, but this really works with really anything, anything that can be easily combined, but is difficult to separate. Right, anything that can do that, or any operation. I'm going to rephrase any operation that is fairly easy to do, but incredibly incredibly time consuming to undo. Right? So with this idea, this Diffie-Hellman key exchange, right, is this idea up here as a concept. We can bring this down to mathematical levels and think about things that are easy to do and incredibly difficult to undo. Right? Now, something that might be fairly easy, right, and that we're going to use as our keys are going to be like multiplications of numbers. So if I gave you, this number over here and this other number over here, right, these two numbers, given enough time, you'd be able to do this multiplication. Now, you have the tools for this, right? Even I'll make this smaller too if we want, right? Like, this shouldn't take you too long to do, right? And getting a computer to do it, right, it's just automating the steps that you would do anyways. Now, multiplication is something that's not too hard, but factorization, right? Factorization is actually really difficult. Factorization is going to mean taking a number and breaking it into, two numbers. For us, it's going to be two numbers that multiply to make that first number. Right? Two numbers that nicely, two nice whole numbers that you can multiply together to make a number. Factorization is hard. Prime factorization is even more fun. Finding the two primes that need to be multiplied to get you to a particular place. So when people are trying to put together these common secrets and their secret keys, what people might tend to do, right, or the strategy is to look up gigantic prime numbers. Let's find a really big prime number. The largest known prime number by year. I mean, if we even just look at how many digits these prime numbers have. Oh no, right? Right, like these things are genuinely terrifying. And it's kind of funny when you start looking into prime number search. What? Just this idea is bizarre, right? When you start looking into prime number searches, here's an article, January 19th, 2016. Good news, everyone! Largest known prime number, 2 to the 74,207,281 minus 1. It's prime, just in case you were wondering. It's prime. Looks like we can move on to finding the next one. Right? Let's keep searching. Look, GIMPs finding world record prime since 1996. I like the formula technically for generating primes, or rather numbers that might be prime, is 2 to the p minus 1, where p is any number. It may be prime. Maybe. We make a number that might be prime, and then there's a whole series of operations you have to go through to eventually find out if it is or isn't. Now, the thing that's beautiful about this is, say I got this number, which you can actually see if you go to like there's, oh, there we go. I just downloaded it. Just downloaded that Mersenne Prime. Let's take a look. Let's crash my computer. Here it is. I don't want to put it in VS Code because I honestly think VS Code might die. Let me just. All right, so here is the largest known prime number known to humankind, and we'll just keep going. And I'd like you to keep your eye trained on this as I scroll. I'm scrolling madly right now. Like, I am scrolling madly. Here are, I mean, this is a number. Like, this is a number, right? And it's prime. It's fantastic. Because this means that this number here could be factored into 2. Oh, wait, shit. No, no, sorry, not factored into 2. This number and another number similar to it, right? Like another number that's just as big as this could be multiplied together to make a number that isn't prime, right? But is made up of 2 primes, right? So ideally, I would take this number here and maybe multiply it against itself, or multiply it against, 2015's biggest prime, right? And we would use that as that like combined combined thing. Now, if you were asked to divide a number and find these factors, I could just imagine that like your head would explode, but also any machine, any normal machine is going to scream and give up, right? So if this is our operation here, we're fairly safe in saying, hey, multiplying 2 things, fairly easy, right? Fairly easy, but dividing them, like factoring, that can be a heck of a nightmare. And you know what's beautiful? I have this gigantic number. You want to see something sneaky? Whoop, not prime anymore. Haha. Right? A little bit of sneakiness. These things are very, very particular. Right? So that's what we'll use for the Diffie-Hellman key exchange is there's libraries out there just like I did right now. I can go look up prime numbers, right? I can go look for 2 prime numbers and multiply them together. Right? I could look for 1 prime number and make it public. I could go look for another prime number and keep it secret, multiply them, send them out, right? And there I've initiated my key exchange, right? These things are public, they're out there, right? You can go to a library and find a book, but it's virtually useless in terms of undoing. Cool. Does anybody else just get a sense of like existential dread when you look at something like this? It's like tapping into some kind of eldritch horror. I don't know if anybody here is into... I don't know if anybody's into like... Is eldritch horror like, oh, it's like a board game? I don't know if anybody here is into like H.P. Lovecraft. Like, it just gives me this feeling. Like, just madness. I don't know. Ugh. So, what we're going to do is I'm going to say one thing, leave you with a thought, and then we'll pick it up when we come back, which is this. The Diffie-Hellman key exchange, we had unanimously, the 2 of us at least, agreed, is called the Diffie-Hellman key exchange because it was developed by, probably Whitfield Diffie and Martin Hellman, right? Obviously, is Whitfield a common name? No? Whitfield Diffie and Martin Hellman. Then you look back a little bit, you're like, oh, conceptualized by Ralph Merkle. Ralph Merkle. And we start digging a little bit deeper into the history of the Diffie-Hellman key exchange. And one thing that we might find out is, where we go? Let me make this big because, I mean, this is straight up conspiracy theory stuff. The scheme was first published, in 1976. But in 1997, it was revealed that James H. Ellis, Clifford Cox, and Malcolm J. Williamson of the GCHQ, the British Signals Intelligence Agency, had previously in 1969 shown that this kind of cryptography here, which I'm going to call public key cryptography, could be achieved. So the Brits, they knew this. They knew this for years. Like genuine years, they knew this math stuff, but they kept it a secret. Now the deeper you go into this, the more you realize that the Diffie-Hellman key exchange is one of the things that makes the internet and that makes networking between computers fundamentally possible, right? Like secret, like private networking, it makes that fundamentally possible, right? And the fact that the GCHQ had kept this stuff a secret for so long, right? I mean, 1969 and 1976 is not a short amount of time. Right? The fact that they kept that secret for so long, how far back did that hold us? Right? And what other kinds of secret math is being hidden? Right? That's something that I want us to think about, and we'll dive into when we come back from the break. Right? Any questions? No? Secret numbers. Cool. So we're gonna take a. How about we take a 10-minute break? Come back at 10:09. Right? And we'll dive a little bit deeper into cryptography. Cool. Is it? How do I never get the math right? We'll come back at 10. We'll come back at 10, and we'll start up again. I'm glad I have you here. Yeah. It's got like a Uncharted feel to it. I mean, it looks pretty cool. There's Danny Trejo is in it, obviously. Yeah. Yeah, he's not in the trailer, but like, and then it's like she has a knife. Yeah, it's like genuinely pretty hardcore, and like. There's a live action monkey for boots. Well, okay, it's like a CGI, but like it's supposed to look live action. This is cool. You're right on time. We're gonna watch the Dora the Explorer trailer now. Yeah. So today, so far, we've learned about really big numbers, exchanging secrets, and we're gonna dive into a couple more things. I guess when we finished off, oh, if you want to see the math behind the Diffie-Hellman key exchange, here it is. But it kind of centers around this idea. You know, multiplication of numbers that are prime, or like involving numbers that are prime, in one way or another. The Diffie-Hellman key exchange, it allows us to do something that we'll call public key exchange, which is the basis for public key cryptography, right? Public key cryptography means that there's some information that is made public to everyone, and maybe there's also secret information, and that'll be useful for a couple different things. If we were to look kind of back here at the goals that we'd set up, we now have this one done. How can Alice and Bob exchange the keys in a non-dumb way? Right? This was a Diffie-Hellman key exchange. Right? You can start digging into some of the other stuff, the sending secret messages and ensuring that the messages they receive are actually from Bob and Alice. Technically, this stuff here now, how can Alice send secret messages or how can Bob send secret messages? Technically, we've already done that now, right? With the rote 13 or, you know, whatever cipher that we want, right? So instead of rote 13, it would be like rote X, right? Whatever cipher we want, we've technically figured that out. But it's not very robust in the sense that if I start sending messages back and forth, hey, what up? Not much. You, I'm at your window, right? Like just normal messages between friends. When you send enough text, right? When you send enough text, you're going to start seeing the letter E show up all over the place, right? Now, E is like the most commonly used letter, like statistically, in English. So if we had some kind of cipher like rote 13 or rote X that takes a letter and then just maps it to another letter, you know, once we've got like an established kind of backlog of information of like messages that are encrypted that maybe I've sniffed out, I can still do like statistical analysis on that stuff and find out, okay, the most common letter that pops up in there, just replace it with an E. Right? Second most common letter, replace it with an A or whatever, and make my way down until eventually I've got something that starts looking kind of like, you know, can I buy a vowel or whatever. Like it's just Wheel of Fortune at that point. So we would like an algorithm that's a little bit more complicated and it doesn't just do letter to letter kind of translation, and instead does more of like actually transforming input to something else. So that kind of stuff can be done with a bunch of different like encryption algorithms. You've already kind of used that stuff a little bit. You used bcrypt, right? You used bcrypt, and the input you gave was completely irrecognizable from the output that came out. So we are going to talk about a thing called RSA. We're not going to look too deep into the math of it, right? But we're going to talk about RSA being the RSA is over here. RSA. Rivest, Shamir, and Edelman. It's one of the first crypto systems. A crypto system would be like a collection of algorithms that make up an entire system for encrypting and decrypting and sending messages back and forth. It's one of the first public key crypto systems, and it's still widely like used for transmission of data securely. So a crypto system for us, such as RSA, is gonna rely on a couple things. Can somebody help me move this dude over, and then I'm just gonna erase this stuff. Thanks, dude. Whoop. All right, grab a little eraser. Little. Can you grab a pen too? One sec. Okay, both of these are kind of trash, but we'll make do. Ooh, can you test those out? That's pretty good. Kind of garb. All right. Cool. So, coming back to that idea of Alice, Bob, and Eve, I've got Alice over here trying to send a message to Bob. And then there's Eve in the middle who's trying to like intercept messages and maybe read them. Eve might also be trying to intercept messages and maybe like tamper with them. Now, we had two questions that we're going to address with the RSA system. And the two questions were, how can Alice send a message to Bob secretly? Right? How can Alice receive messages from Bob secretly so they can't be read? And then the other thing is, how can Alice ensure that the message that they're receiving is actually from Bob, and vice versa? Right? So RSA is going to help us do this with the introduction of, oh my god, this pen is garbage. With the introduction of using these public and secret keys. So Alice is going to start by generating a public key and a secret key that are actually paired, right? These things get spawned together, right? So in as an example, and this isn't exactly how it works underneath, but I showed you that we can have like a really big number that can be factored into primes, right? For example, the number 10, a big number, not a prime number, but I can factor it into 5 and like 2, which are prime, right? So, there might be these two things that are, done together or whatever. In the same way, there's a method for generating two keys that are intricately kind of tied together, right? One of them is the secret, or I'm going to call it the private key. One of them is the private key that Alice is going to keep here, and the other one's going to be a public key. And the public key, Alice will tell everybody about. Alice will tell everybody about, and when I say tell everybody, I mean very, very seriously. Like, if you go see, like, some people's web pages, for example. So this person's Drew DeVault. They're like a blogger, software developer person. But you might notice in a lot of cases is people will publish public key on their websites and make this stuff like readily available. So this is his blog, and he's put it right here. And you can click on it and see his entire public key. Right? This is his entire public key, and he's made it public. Right? If you go download like some things like the Linux kernel, for example, if we were to go to like download, so Linux kernel is the thing that Linux operating systems are built around, like Ubuntu or whatever. Anytime there's a new release of this, or anytime there's a new release of really any software, you'll find the download link. In this case, they've called it a tarball. It's just a zip file. But there will also be a PGP verification signature, right? And in this case here, this is going to be something like a public key. And if I look at this, it's going to be another one of these things. So People are very, very vocal about the fact that, hey, I have this key. Everybody know I have this key, right? So Bob knows that Alice has this public key. Eve knows that Alice has this public key. And then what Alice is going to do, right? What Alice is going to do, and this is in this direction right now. When Alice has a message, I'm going to call that message X. Alice is going to encrypt that message. Is going to encrypt that message using the private key and the RSA algorithm, right? Which is similar to like, kind of what we did with the, coming up with a system. The RSA algorithm, it's public knowledge, everybody knows it, but it depends on knowing these two keys to actually do anything useful for it, right? So Alice is going to encrypt it using RSA and their private key, right? And they're going to send that message out. Eve might very well be able to take this message, right, which was encrypted with the private key, right? Take the message that's encrypted with a private key, and Eve is able to use Alice's public key to read the message. Eve is able to do that and actually read the contents on the inside, right? So Eve can read it, and so can Bob, right? So if Alice wanted to send it to Bob, like Bob can use the public key to unencrypt the message and get the actual message out, right? The interesting part here, though, is that if Eve receives the message, right, like steals the message, sniffs it, reads it, and then tries to edit it a little bit, Eve is not able to package that message up again and send it to Bob, right, to trick Bob into thinking that Bob had received like the original message from Alice, right? So if we were to think of, applications of this in web development, right? You could think of like bank information, right? I'm sending like a bank, like money transfer or whatever, right? Alice might originally have sent saying, hey, I'm sending you $5, right? Alice is sending Bob $5. And then somebody sneaks in, unpacks the message and changes it to say $10 instead, right? Or $3 or whatever. Eve is not able to close that up and send it to Bob, because if they do, when Bob gets it, right, Bob's not even going to be able to unencrypt it because Eve did not have the private key that's necessary for encrypting. Right? You can only use the public key that was paired up with the private key. Right? So in this case here, we've figured out how to have communication that is assured, right? Like it's certified that this message is coming from this person, right? So Bob can be sure that the message is coming from here. This is part of why when you look at a website, you see the little lock icon, right? And it says the connection is secure, right? This is going to mean that like part of what this means is that any content that you receive from this web page, right, is going to be actually from the servers that they said they are, right? They've had to deal with like third-party certificate granting agency, right? They've actually had to interact with somebody to verify that these are my machines, this is my code, and all that, right? And now they have the little lock that says, hey, you know what? If you're Bob and you receive something from Alice, like I am Alice. So RSA lets us do that, and what RSA also lets us do is use the public key that had been published by Alice, to send Alice secret messages. Right? So Bob is able to use Alice's public key, encrypt a message, and send it to Alice. This way here. Right? So Bob can encrypt a message using Alice's public key. Eve is not able to unencrypt that because Eve does not have the private key. Even Bob is not able to unencrypt their message because Bob doesn't have Alice's private key. And now this way we've set up with a private public key pair and this RSA algorithm, which again is just a bunch of math. It's just going to take an input and do something and give us an output. We've set up a thing where Alice can send verified messages and Alice can receive secret messages from anybody. Right? And this all happens around this whole public key system. Right? If Bob had their own public key that they put out there and their own private key, then Alice could also use that to message Bob secretly. Right? And we could have two-way secret communication. Right? RSA. Are there any questions about this? I think this stuff is like supremely fascinating because the RSA algorithm, you can use the private key to do a thing and you can use the public key to do a thing, right? And it's this like dual kind of forest algorithm that does both, right? It's pretty beast. I mean, it's a fairly simple idea, and when you dive into the math, if you have a little bit of a math background, it's actually not very bad at all. Right? And it is the foundation for how communication happens in a certified, like assured way and in a secret way on the internet. Right? Because so much of our communication needs to happen in that secret, assured way. Right? If I am sending a message to Twitter, like Twitter better be sure that I'm the one sending it and not somebody who's just using my name. Right? So you're not going to be dealing with the math directly, right? But what you will be dealing with in your life, right, as web developers is maybe setting up certificates, right? Like maybe setting up SSL certificates. Right? And I want you to know that underneath, like, when you go into looking at what an SSL certificate is or whatever, right? It's the thing that lets you get this lock on your website and lets you use HTTPS for secure. Right? What's going on underneath is that you're generating a key, and you're verifying that that key is yours with a third-party kind of like organization, saying, "Hey, this is me," so people can have that kind of secure and secret communication back and forth. Cool. Is this stuff like vaguely kind of cool to anybody? It's pretty neat. I would really recommend taking a look at there's like 3 blue, 1 brown. I don't know if anybody knows. Does anybody know 3 blue, 1 brown here? So 3 blue, 1. I guess there's not a lot of like. Y'all don't watch math videos on YouTube for fun. 3 blue, 1 brown is this person who puts together these like really, really good math and computer science videos. So like they have this really great kind of series on neural networks, some great videos on the math behind cryptocurrency. Right? So if you're particularly interested in blockchain or cryptocurrency, like a lot of it does kind of hinge on part of this idea that we've talked about of things that are easy to do and hard to undo. In fact, here in this video, what do you think PK and SK stand for? Public key and secret key, right? So this stuff is really kind of all over the place, and I really recommend watching his videos at some point. They're really relaxing. Okay, so are there any questions about this stuff? Do you see what I mean when I'm like, you're not going to be doing this in like assignments or whatever, right? But it's still really cool, right? The world of computer science is this stuff. So just in case there were any lingering kind of confusion about what computer science is, because I know for a lot of people, like a lot of people think computer science is programming. A lot of people think computer science is web development. It's not. Computer science is this stuff here for the most part, right? Computer science is figuring out like the math underneath that enables your computers to actually work. This seems interesting. Like, come talk to me and I'll show you some of the like course materials that I have from like the courses I've taken, if it's something that you're interested in, like reading up on after boot camp. I have a ton of resources. Now, there's 2 videos that I want to take a look at, are sort of tangentially kind of related to this. This whole idea, RSA, public key encryption, Diffie-Hellman, it's all for setting up the fact that like communication needs to be secret, communication needs to be authentic, right? We need to ensure that I'm talking to the correct person. We've already done parts of that with like passwords and whatever. Right? There's a couple different additions, like additional layers for security that we'll have to do, right? Such as, you know, when I signed up for Facebook earlier, like I had to set a password. Right? A password is like one method for authenticating a person, user, for authenticating. So authenticating and authorizing are two different things, right? I think you get used interchangeably, but they're two different things. Where authenticating is the user is who they say they are, right? Authorizing is the user has access to particular things, right? Two different things. I could be authenticated, but I could not be authorized. That's fine. So when we're doing like username and password to get into a page, part of that process is authenticating. Is this person who they say they are? And we can do that with one factor. And that factor is, do they know a particular thing? Do they know a word? Right? We can have multiple factors, right? We've all heard maybe of two-factor authentication. What do you usually have to do when you see the word two-factor authentication? Yeah. Right, receive something from them and then return that stuff. Now, fundamentally, like this is the action that's happening, right? Like when we say two-factor authentication, often what that means is like you receive a text message with a code, right? So you're trying to log in somewhere, and Google's like, "Oh, we've sent you a text. Please enter the text that you've found," right? Like the code. But conceptually, the reason that we want to do this is so that we don't just check what a person knows, right, such as a password, but also what a person has, such as a phone or a laptop or a tablet, right? We're checking two factors to authenticate. Do they know a particular thing, and do they have a particular thing, right? It's like a physical key, right? You need to have a particular key in order to enter a house, right? Ownership, right? And here we've gone into, you know, multi-factor, maybe just two, right? But the industry doesn't, or like conceptually, we don't just have to have two. A person can know things, a person can have things, and maybe a person is a particular thing, right? Like we might be talking about like biometric stuff, like blood samples or fingerprints, right? A fingerprint is a thing that a person is, like it owns that. This is part of who I am. And now we've hit onto like multiple factors. So, you know, when you're using your phone to like log into your phone with your fingerprint, right? That's a different factor than maybe something that you know, right? And by combining all these factors, it becomes harder for somebody to hack into a system, because they don't just need to know your password, they also need to own your phone, right? They need to have access to your phone, or they need to have access to your fingerprint, right? So this stuff is actually like supremely interesting, and I recommend doing some readings into, because the more complicated this gets, the harder it is for people to hack into systems, right? Sometimes people find odd ways or surprising ways around systems, even when we put big checks on them. So, for example, there's this person called Barnaby Jack. So, yeah, Barnaby Jack. So Barnaby Jack was a hacker from New Zealand and an expert in computer security. And they were particularly famous because they would do these insane demos at computer security conventions, such as this demo here, where Barnaby Jack brings on two ordinary ATMs and has them just like return money. Like, these are ordinary ATMs, and he hacks them to, like, print out money. Right? So somehow he hacked them. Right? And it's just bizarre. Like, it just keeps printing out money. Another thing that Barnaby Jack did was showing off how people could exploit medical devices remotely. So, like, I could be here, and somebody with a pacemaker or an insulin pump could be over there, right? And Barnaby Jack had shown that, like, that stuff can be hacked remotely, and you can stop a pacemaker, right? Or you can start, like, an insulin pump, right? Remotely, right? Scary stuff, right? But it's good that it's being shown off so that, like, computer security experts can continue to, like, build on top of that and make sure this stuff gets more and more and more secure. Jack died in 2013, and it's a bit kind of weird. I'll invite you to just kind of read into it, but really kind of interesting person. Right, so hacking can happen in all kinds of ways, in all kinds of, like, strange situations. For example, there's this video here. This person goes to, like, the person narrating the video went to a conference called, or a convention called DEF CON. DEF CON is a convention where hackers get together and they talk about hacky things. And this is one of the people that this person met. There's, like, subtitles, but I'm going to put the audio up as much as I can.
So I invited a few of the world's best hackers.